Hi all, today we will discuss about a special type of memory called associative memory. So in general, how a memory is organized means, as we discussed earlier, the memory is divided into different memory locations, and each memory location is called a memory word, and each memory word has a unique address. So using this address, uh, one can easily identify the location of the memory word. So to search a particular data in a memory, data is read from certain address. Definitely, it is required to have an address to find a particular data or memory word in memory. And that address, for example, the memory address register contains the address of a particular memory location that you want to read or write. So the now this address that is present in the MAR is compared with let's assume this is my address. MAR is a register and it has address 105. So here 000, 001, 011, 100, 101. This is a let's assume this is memory which is divided into five different memory locations, and the MAR is a memory address register which contains the value 5. So this 101 is compared with each address. So the best way is, if you look at MSB position 1, compare with 1, and next 0, 0 and 1. So this is the memory location that you want to fetch. So to search a particular data in memory, data is read from certain address and compared if the match is found. The content of the next address is accessed and compared. So this is the general procedure in normal type of memories where the address is compared with all the addresses of the memory. This goes until required data is found. So this procedure, if the match is not found, the content of the next address is accessed and compared. This goes until the required data is found. The number of access depends upon the location of the data and efficiency of searching algorithm. This searching time can be reduced if the data is searched on the basis of content. So here what's happening, if I have a memory address register and this is the memory that is divided 0000001 011 100 101 20 30 40 50 and 60. So in data, to search a particular data in memory, data is read from certain address and compared. If the match is found, the content of the next address is accessed. So but what happens in a special type of memory called associative memory? There is no concept called addressing. Directly the MAR contains part of the data. Let's assume this is 20. So it contains the part of the data. If 20 is represented as 1, 8, 1, 2, 4, 8, 16, 1, 0, 1, 0, 0. Let's assume 20 is represented as 1, 0, 1, 0, 0. So the part of the data is stored here 101. This is compared with the data. This is called a special type of memory called associative memory. And the goal of the associative memory is to reduce the searching time. Next, to search a particular data in memory, data is read from certain A memory unit accessed by content is called associative memory or content addressable memory. So if the memory unit is accessed by the content of its own is called associative memory, or associative memory has a special name called content addressable memory. So what happens with this content addressable memory, or you can call it associative storage? This is called associative storage or associative array. So it has so many names. This type of memory is accessed simultaneously and in parallel on the basis of the data content. So the goal of the associative memory should be the searching time of a memory word in a memory should be reduced. So how it reduces this type of, it follows the simultaneous and parallel processing of comparing of the data. So this type of memory is accessed simultaneously and in parallel on the basis of data content. Memory is capable of finding empty or unused locations to store the word. So even it is not only useful, the content addressable memory or associative memory is just not only useful for searching particular word to read operation. In fact, it is also used to perform the write operation with less amount of time, because using this technique uh, in less amount of time, the unused or empty location or empty memory location in memory can be found. So this is the advantage of uh, content addressable memory. And of course the disadvantage is that it requires some extra hardware to follow the technique of content addressable memory, finding the data based on spot of the data or whole data. This is an introduction to associative memory. Now let's see in detail about this. So this is about associative memory organization. So here what happens, we have a special register called augment register. So this argument register contains the data that you want to search in associative memory. And there is another type of register, two special type of register, which is called key register. This is called argument register, and this is called key register. Now this is the associative memory. This is the actual associative memory, which contains some m words. It contains m memory words, and each word contains n bits: 0, 1, 2, dash 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 n minus 1. So like that we have m words. So what happens, let's assume you want to find out 10100001. Only part of the content is placed in the key register, and simultaneously this is compared with all the memory words, and whichever matches that is set to 1, and which doesn't match will set to 0. And this is a read based on input signal read operation or write operation. Signal is sent to this type of memory. So it is very important to understand how memory is organized. Let me repeat once again. It contains 0, 1, 2, dash, 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 n minus 1 bits, total n bits words. Such type of words would be around m words. So it contains around m words. So the argument register and the key register are the two special type of registers, and match register is like a group of flip-flops. If a particular data location, the memory word contains the data in the key register, then the match register is set to 1. If it doesn't matches, then it is set to 0. So associative memory is organized in such a way. There is a special register called argument register, and this argument register contains the word to be searched. So it contains the word to be searched. It has n bits, one for each bit of the word, one for each bit of the word. So its length is n. So argument register length is n. Next, we have a special type of register called key register, and the key register specifies which part of the argument words needs to be compared with the words in the memory. It is really a great challenging to place what to select which part of this n bits. Remember, argument register contains n bits, and key register selects some bits out of this n bits, and so it specifies which part of the argument, whether you want to see the first k bits. Obviously k is less than n, so you want to select which part of the word, whether first k bits or last k bits, something like that. So the key register contains k bits, and these k bits are a subset of n words. So this specifies which part of the argument word needs to be compared with the words in the memory. If all bits in the register are 1, the entire word should be compared. Otherwise, only bits having k bits set to 1 will be compared. So this is interesting one. So if this is my argument register, it contains n minus 1 bits, and there is a key register. This key register also contains n bits. Key register also contain n bits, but if the corresponding location is 1 in key bit, then this bit has to be compared. If it has 0, you don't consider the bit. So the key register basically contains some k bits to be 1 all the time. So whichever the position 1 is there, the above argument bit corresponding above bit in the argument register should be considered for searching a word in the memory. So this is how it works. And if the key register contains all ones, so if the key register contains all ones, that means you have to consider entire argument register should be considered. The content of that means you have to consider all n bits for searching for a particular word, which is not advisable. In general, the key register should contain some zeros. because sometimes the length of the word may be very long. N bits mean 32 bit. So you don't compare. It's not advisable to compare all 32 bits in the argument register. So let's assume there is an argument register which contains 0 to 31 bits. So it's a 32 bit register. And of course the key register, this is the argument register. The key register also contains 32 bits. But it is not advisable to have all ones in 32 bits of key register. So at least some parts should be 0. Then we can say that this fulfills the purpose of associative memory, which has an advantage that it takes less amount of time to search a particular word. If the key register contains all ones, then it is not advisable because it may take longer time than normal memory organization. So this is about key register and argument register. Next we see another components in the associative memory, that is associative memory array. So this associative memory array, it contains the words which are to be compared with the argument words, and it contains n bits. Each memory word contains n bits, like that m words. But it is not advisable that the m should be very greater value. Then it is this content addressable memory technique can be applied only when the memory words are limited in the memory, like cache memory. And there is a special register called match register. It has m bits because how many number of words the associative memory contains, those 0 to m minus 1. So there should be a match register which should contain exactly 0 to m minus 1. So what it is used means, so it is basically used to uh, see that if a particular word is matched with its content, then corresponding so the match register contains m bits. It contains equal number of bits that memory is divided into memory words, m words. Then the match register contains m bits. If the corresponding location contains the content of the argument register, then the match register corresponding bit is set to 1. So it has m bits, 1 bit corresponding to each word in the memory array. After matching process, the bits corresponding to matching words in match register are set to 1. And remember, there can be more than one bit set to 1 in match register. So this is about associative memory. And let me repeat, the advantage of the associative memory is that it is used for fast accessing the data. Especially it is used to manage the cache memory. But the disadvantage is that it requires some extra hardware like argument register, key register, match register. And this technique is advisable to apply to only the memories which have less number of memory words. Now let us discuss another important concept, very important concept in computer architecture, that is called virtual memory. So it's really important to understand the meaning of the word, the virtual. So virtual means something not real. It's an illusion. This is the general English dictionary meaning of the word virtual. So you might have seen in recent trends a word called virtual reality. See, in near future, Reliance Jio is going to introduce the 5G technology. This 5G, using this 5G technology, you can experience virtual reality. How virtual reality works means, now what's happening when you are speaking, when you want to speak with a person, you are making a call over the phone. But with this virtual reality technique that is supported by 5G, you can feel that the person is sitting right in front of you. The person is just in front of you. This is called virtual reality. In fact, the person is not in front of you, but you will feel like you can see that he is in front of you. So this is one kind of illusion. That is the meaning of the word virtual. Similarly, here we are discussing about virtual memory. Virtual memory is like an imaginary memory. You can say that virtual memory is like a imaginary memory. So virtual memory means an imaginary kind of memory. So virtual memory is an imaginary memory which we are assuming uh, if we have a material that exceeds your memory at that time, we need to use the concept of virtual memory. So uh, what is the need for developing this virtual memory technique means, let's assume you are sitting in front of a computer and you are the software developer you are to develop some program. Let's assume my main memory capacity is 4 GB, and this is 1 TB, that is 1024 GB of hard disk, and some processor you are using. Let's assume it is i7. So you want to write a very large program. Your manager asked you to develop a very big program, and it then and that program much bigger than the capacity of your RAM. Let's assume you want to develop a program of 5 GB. Obviously, you cannot store this 5 GB program in 4 GB RAM. But if you want to execute this program, see what happens when user develops a program. This 5 GB program will go and sit in the hard disk secondary memory, but when you want to execute it, that has to be brought into or transferred into RAM, which is not possible because of its size. It is 5 GB, which is bigger than the main memory or RAM capacity, that is 4 GB. So what should happen? What whether your system should give a error kind of thing that you are allowed to develop only the program whose size is less than 4 GB. In general, you can't see such error. Why? Because your computer has a technique that is implementing, that is called virtual memory. So now you understand. So the user, or the developer, or the programmer was not constrained, or was not limited to develop the program whose size is less than main memory. He can develop as much as bigger program he want. In fact, he can develop a program whose size is as equal to as its hard disk capacity, that is 1 terabyte, that is 1024 GB. So there is no constraint. How it is possible means using a special technique called virtual memory. So now you better understand the concept of virtual memory. Virtual means it's not real, it's an imaginary one. The virtual memory means the developer or the programmer feels that he has 1024 GB of the memory, and he can develop a big program whose size is as equal to 1024 GB, and he can execute that program. The specialty is that he should be able to, the developer should able to execute, the system should be able to execute the program of the capacity 1024. So a developer can develop a program whose size is equal to its hard disk capacity. But how can this program be executed? Yes, of course, one programmer or one developer can develop a program whose size is as large as a hard disk capacity, that is, in this case, 1 TB. But how is it possible to execute the code? Yes, it is possible using a technique called virtual memory. Now I think you understand the concept of virtual memory. So here what happens in virtual memory, the developer feels that he has a RAM whose capacity is equal to the hard disk. That is he has the RAM capacity of 1 TB. He has 1 TB RAM. So how it is possible using a special technique called virtual memory organization. So virtual memory is an imaginary memory. Imaginary memory means the developer feels that he has 1024 GB of RAM or 1 TB of RAM, and he is free to develop a program as much as bigger as he would want to, and the system ensures that your program will get executed without any constraint. The how it is possible means just make the program into small chunks, divide the program into small pieces, and call each piece first a process, and similarly divide the RAM main memory into small pieces and divide the hard disk into small pieces and call these pieces as pages. So this is a technique that is used. That is, main memory is divided into number of pages. Similarly, hard disk is divided into number of segments or pages. Now, whichever part of the program you want to execute, place that in the RAM. And remember, the page size cannot be more than main memory capacity. That in this case, the page size cannot be greater than 4 GB. Let's assume the page size is 1 GB. Then your main memory is divided into, let's assume this is my main memory whose capacity is 4 GB. Now my main memory is divided into four parts, 0, 1, 2, 3. Of each part is called a page. So each part is called a page and its size is 1 GB. 1 GB of page size. So this is the logic behind how virtual memory works. So the virtual memory is a temporary memory which is used along with the RAM of the system. And what is the importance of virtual memory? Just now we discussed. When your computer runs out of physical memory, so physical memory means RAM. So when your computer runs out of physical memory means main memory or RAM. When your computer runs out of physical memory, it writes what it needs to remember to the hard disk in a swap file as a virtual memory. If a computer running Windows requires more memory or RAM, then there is installed on the system to run a program. So it uses a small section of the hard drive for this purpose. So this is about importance of virtual memory. Now there are two important words related to virtual memory, that is address space. So the virtual memory is the address used by the programmer, and set of such addresses is called virtual address space or address space. So it is called virtual address space. Space means group of addresses. What type of addresses? They are virtual addresses. They are not real. They are not real addresses with respect to main memory. If you go, if you take the particular virtual address and try to search for that particular address in the physical memory, main memory, you can't find, because it's not a real physical address. It is a virtual address. So virtual memory is the address used by the programmer, and set of such addresses is called address space. Let me give you an example of what is meant by virtual address exactly. Let's assume this is my hard disk. It is divided into 20 parts, 0 to 19, 0 to 19, so 20 pages. Let's assume each page size is 1 GB, so it's a 20 GB hard disk. Now I have a main memory which is divided into 4 parts, 4 pages, 0, 1, 2, 3, and each page size is capacity 1 GB. So now what happens? The programmer has no restriction that he should use the address of any of these 4 pages. So he can have the page number 0 to 19. He can use any page between 0 to 19, and within that page he can he can search for any memory word. So if the user or developer issues an address in that 20 means we can represent with 5 bits, right? 0, 1, 2, 3, 4, so 5 bits. Or you can say that 20, how many bits are required to represent 20? Obviously 4 5 bits. So the first 5 bits represents the page number, and the remaining specifies the address within that page. But in fact, let's assume I use a word which has page size of 15, the page number 15. Page number 15 means all ones, 4 ones. This address is called virtual address. Why? Because if you take this address and try to find out the page numbers in main memory or physical memory, you have maximum 3 pages, 4 pages, but you can't find 15 page. So this set of addresses, indirectly the set of addresses of secondary memory, is called virtual address space. And in other way you can say the set of addresses used by the programmer is nothing but virtual address space. And an address of main memory is called physical addresses. These are the physical addresses, actual addresses. So virtual address means the address issued by the programmer is called the address issued by the programmer is called virtual address, and the set of such addresses issued by the programmer is known as virtual address space. Is called virtual address space. So virtual address space means the set of addresses issued or used by the programmer is called virtual address space. Now what is another term called physical address space? Remember, whenever you use a word physical, it is related to main memory, that is RAM. So the addresses in main memory is called physical address space. So very simple definition. The addresses in main memory is called a physical address. A set of addresses that refer to main memory is called physical address space. So the set of such locations in main memory is called physical address space. Thus, the physical address space consists of actual main memory locations directly addressable for processing. So, the addresses issued by the programmer, the set of addresses issued by the programmer is known as virtual address space. The set of addresses of main memory is called physical address space. Now let us see, before going to discuss how virtual memory works, let us discuss what are the advantages of the virtual memory. So the advantage of the virtual memory is that it allows processes whose aggregate memory requirement is greater than the amount of physical memory. So what the greatest advantage of the virtual memory that it allows the processes whose memory requirement is greater than the amount of physical memory. Physical memory means RAM. As infrequently used pages can reside in the disk. We'll discuss what is the term infrequently used pages. Virtual memory allows the speed gain when only a particular segment of the program is required for execution of a program. So the another advantage of the virtual memory is that the execution speed increases only a particular segment of the program is required for execution of a program. That means if you want to execute a program, it is not required to have total program to be present in the main memory. Only the part of the program we'll call a special word is process. So remember, a process is nothing but a part of program. Like you divide the main memory and secondary memory into pages, the program can also be divided into a unit of execution called process. And processes can be executed independently. So you should divide a program, so that program should be divided in such a way that they can be executed in any order. Let's assume this is my program. If this is my program, and this program should be divided into processes P1, P2, P3, P4. So these P1, P2, P3 and P4 are called processes of this program. So what is the definition of a process? It's a part of a program that can be executed in any order So P1 can be executed before P2, or P2 can be executed before P1, or P4 can be executed before P1. So the program should be divided in such a way that it can be executed, its parts can be executed in any order. And it's really a great technique. And who will do means your operating system. It's the job of your operating system to divide a program into a number of processes that can be executed independently. But the only constraint is that a process should be able to store in one page. So in general, the size of the process should be less than or equals to page size. So far we are saying that program should be divided into some processes, and processes is some unit of execution that can be executed in any order, at any order. This is called a process. And when you divide the main memory into a number of pages, in general, the general rule is that a page should accommodate one process at least. It can accommodate, of course, two processes, but the goal is that one page, the size of the page. If somebody asks you what should be a page size, the page size should be in such a way that it can be executed, it can store at least one process. The size of the page should be in such a way that it can accommodate at least one process. Of course, it can accommodate more than one process. So this is about program and process and pages. So in this scenario, let's assume this is my main memory. So I divided my program into P1, P2, P3, P4 and P5 processes. And my physical memory means main memory or RAM, is divided into four processes, four pages, and my hard disk is divided into some 20 pages. So at any time, the requirement is that the page size, the page can accommodate at least one process. It's really important to understand how it works. So one process can store at page 1, another process can store at page 2, another process can be stored at page 3, another process can be stored at page 4, and this P5 has to be present in secondary memory. Now if the CPU means the processor issues an address that you want to execute an instruction related to P5. P5 is not in the main memory. So the programmer issued an address which refers to the page which is not available in physical memory. Rather, that page is available in secondary memory. So this situation, that desired address, when a programmer issues an address, the processor issues an address such that it belongs to a page which is not present in the physical memory. This situation is called page fault. It's very important to remember this word, page fault. So we have discussed about virtual memory. What is virtual memory? What is virtual memory? Virtually means not real, or you can call it as imaginary. And virtual address space, virtual address space, the set of addresses issued by the programmer is called virtual address space. Similarly, Physical address space. Physical address space means the set of addresses of main memory are referred as physical address space. And another important word called page fault. Page fault is a situation where the processor issues an address that belongs to a page which is not available in main memory or physical memory is called page fault. So in the next class we will discuss what happens when a page fault occurs.